In this lecture, what we are going to do is we are going to analyze the Otto cycle. We have actually introduced this cycle in the previous lectures itself. However, we have not revised the analysis part of it. So, in this lecture we are going to analyze the Otto cycle. This is not a new material for you. In a way, this is a revision of the thermodynamics course. Part of it was covered, gas power cycles were actually covered in your previous thermodynamics courses. So, in this lecture we are going to see the Otto cycle, and as you know, this Otto cycle is essentially an idealization of the petrol engine, or the other way around. The petrol engine can be analyzed nicely or reasonably well from an engineering perspective. The first level analysis can be done using the Otto cycle. So, let us see the Otto cycle of how it works and how to analyze this cycle to get the efficiency. So, as you will recall, we have 4 processes, that is the compression process, the heat addition process, the expansion process, and the heat rejection process. So, these 4 processes of a thermal engine are represented here on the left of your screen. It is the PV diagram, and on the right it is the TS diagram. Okay, it is the same cycle which is represented on 2 axes here, or 2 different planes. One is the pressure volume diagram, which gives us useful information also, and in certain cases you can get a very good insight and useful information from the temperature entropy diagram also. So, now let us go through the process. You have the BDC, that is the bottom dead center of the piston. So, the piston starts from this position. We can begin the cycle actually. So, from here, from 1 to 2 for example, we have taken an isentropic process, that is a reversible adiabatic process, and the entropy remains constant, and you are actually compressing the charge or compressing the air. In this case it is an ideal gas, which we will assume right now for this discussion. So, an ideal gas is compressed from location 1 or equilibrium position 1, which is the coordinate here, to 2, and it is an isentropic process, as we have already told you before in the previous lectures also. So, this on the temperature entropy diagram you can see it is an isentropic process. So, you go from a certain level of entropy and you compress and you reach at the same level of entropy. If you compress, naturally the temperature will go up and the pressure will go up. So, you are compressing an ideal gas, you are reducing the volume from BDC to the TDC in a real time, let us say, piston mechanism. Naturally this volume here, as you will recall, is the clearance volume. Piston from the BDC to the TDC is the swept volume, and the total volume of the cylinder is represented from 0 volume here up to the BDC. So, this is the total volume, this is the clearance volume, and this is the swept volume between the TDC and the BDC. So, you have reached point number 2. Now, at point 2, as you will recall, we add heat ideally to this system, and this heat addition is at constant volume. So, we give a constant volume heat addition here, and you reach point 3. So, you can see here the volume is remaining constant, all the heat has suddenly come in. We have assumed that there is a mechanism by which it can be done. I will again repeat that in a petrol engine the petrol burns very quickly, and so you can get this heat very quickly between 2 to 3. Okay, so 2 to 3 you have heat addition process, and that is what is at constant volume. So, as you will see, from 2 to 3 you have added the heat, it is at constant volume heat addition, and therefore you have seen volume is equal to constant, and naturally if you add heat to the system, the temperature will rise and the entropy will also rise here. You can increase the entropy by adding heat. For example, this is one way of increasing the entropy of the system. So, you have increased the entropy and you have come to point number 3 in a constant volume heat addition process. Now, from 3 all the heat has come in, the enthalpy has come in, and the piston is now ready to traverse downwards or towards the BDC, towards the bottom dead center, away from the top, and then you can get the expansion stroke. You can get the expansion stroke here. So, this is again an isentropic expansion, which we will assume in an ideal cycle. As I have told you earlier also, in real cycles there will be some heat losses, and we would like to cool the engine also to a certain extent. So, there will be some heat losses, and in subsequent lectures we will see the difference between this ideal cycle and the real cycle also. So, as you can see, expansion has taken place and we have got positive work out of the system. And you have come to point number 4. Now looking the same process in the temperature entropy diagram, you have reached from 3 to 4, and again it's an isentropic expansion. So the isentropic expansion has occurred. Since it is an expanding gas, the pressure is reducing and the temperature is also reducing, and you have reached point number 4, and it's a constant entropy process. So you can see a straight line on the entropy axis. Okay, and then eventually you have to come back to the point from where you started the cycle to make it a closed thermodynamic cycle comprising of these 4 processes. So the last process 4 to 1 is a constant volume heat rejection, and that is what you see here on the pressure volume diagram. At constant volume, if there is a fixed amount of gas which is available to me, and I reduce I keep the volume constant and take heat out of it, naturally the pressure will reduce and so will the temperature be. So as you can see here, from 4 to 1 the temperature reduces, you have taken out heat, so the entropy reduces, and you essentially come back to position number 1. So this is a very elegant representation of an ideal Otto cycle with all the 4 processes. Now you will recall that we want to now get to the efficiency of this cycle. So what is the input to the cycle? The input to the cycle is Q in, and what is the output of the cycle? The output of the cycle is the work done, the net work done. So you can see now in the PV diagram, for example, the area under the curve 1 to 2 will be the work done on the system for compression. So we isentropically compress it. So as I had also mentioned in the last classes also, that we have to compress the gas, and then we need some work to do that. So that work will come from, of course, the engine itself in a way. So from 1 to 2, so the area under this curve, okay, will give you the work which is done on the system. So we have to pay for it actually. That means we have to do it on the system and we don't get it back. But what do we get back? We get 3 to 4. That is the expansion work which we get back, and this expansion work, the area under this curve will be the W out. So the W out minus the W in will be the area enclosed by this particular graph, and the area enclosed by this graph is the net work done by the system. Okay. So we would like, so the input for us is the Q in and the output is the W net. The ratio between the two, okay, what we have got out divided by what we had actually expended or what we had put in, will give you the efficiency. So now how do you calculate and analyze the efficiency of this cycle is what has been explained in the next slide. As you can see here, now let us go process by process. So first we apply the first law of thermodynamics to the entire cycle, okay, and as you will recall that this is the whole cycle and we want to apply now the first law of thermodynamics. So if you apply the first law of thermodynamics, you have the total Q in minus Q out is the net heat interaction on the cycle, and the W in minus W out is the net work done or work interaction on the cycle. So the addition of these two must be equal to the net internal energy, or in this case the enthalpy, if you assume it to be a flow process, then the enthalpy of the system. So and then if you come back to the same point, okay, so it is enthalpy, as you will recall, is a thermodynamic property of the system, that is U plus PV. So this, if you come back to the same state, that means if you go from here, you do several thermodynamic processes, you add heat, you subtract heat, you do work, okay, and then with the same amount of gas you again come back to 1. So if you come back to 1, that means all your thermodynamic properties must be identical at 1. Okay, that means they are thermodynamic properties which are point functions. So when you actually come back to 1, okay, all your thermodynamic properties must be the same, identical. So therefore H exit minus H inlet will be 0. So your net cyclic work must be equal to the net cyclic heat which has gone into the system, as you will recall from your thermodynamics. So now if you can quantify how much is the Q in and how much is the Q out, we will be able to get the efficiency of the system. So let us see the Q in. Now Q in essentially is heat addition at constant volume. That means given a volume, you are fixing the volume and adding heat. Okay, so naturally you will recall the definition of specific heat, that is the amount of energy which is required to raise the temperature of a material, let us say unit mass of the material, by 1 degree centigrade or 1 degree let us say 1 unit temperature. So, this particular let us say Q in will be naturally, there is since it is heat addition at constant volume, that means there is no work interaction in this process. So, naturally the heat whatever you do must be equal to the change in the internal energy of the system, okay. And since no flow is, we are sort of assuming no flow here, okay, it is all the same trapped air which we are trying to compress and do all the thermodynamic process on. So, since there is no W interaction in this process from 2 to 3, your Q in will be equal to U3 minus U2, that is the change in the internal energy of the state of the system of the control volume from the point number 3 to point number 2, the difference between the internal energy. And since it is a constant volume process, and mind you these small alphabets Q, small u is representing per unit mass of the system, for example. So, the CV will be taken as per unit mass. If you are analyzing the system on per unit mole basis, then naturally the CV will have to be taken as per unit mole basis. So, the specific heat at constant volume multiplied by the T3 minus T2 because we are assuming an ideal gas, and the change in internal energy can be directly related to the definition of CV which is del U by del T at constant volume. So, CV into delta T. So, Q in is a heat addition at constant volume, which we can quantify, because if you know the temperatures T3 and T2 and if you know the CV, although it is a function of temperature, but we can assume it to be constant between the temperatures T3 and T2, and you can take a rough calculation and we can take CV as a constant, and you can let us say at an average temperature, and from there you can get the Q in. In a very similar manner you can get Q out, okay. So, Q out is U4 minus U1. So, this is the Q out let us say process. So, naturally at 4 you have higher internal energy. When you subtract heat from it, subtract the heat or take out the heat away from this mass of let us say a fixed volume, then you will reach point number 1, and it is done at constant volume, and therefore in a similar manner as heat addition you can get heat rejection or Q out as U4 minus U1, which is nothing but equal to CV multiplied by T4 minus T1. So, now with this we can since the right hand side here is 0, that means numerically speaking Q in minus Q out, which is the net let us say heat interaction, must be equal to the net work interaction. So, this is W in minus W out is the W net, okay. So, that is the W net which I have defined here. So, the efficiency of the Otto cycle, which is the output which we get as W net divided by the input, W net divided by Q in, which can also be written as 1 minus Q out upon Q in, because the numerator here is nothing but equal to Q in minus Q out, which comes from this equation number 1 here, because the right hand side is 0. So, from there if you substitute the values of Q out and Q in from these two equations at the top, you will end up with this expression for the Otto cycle efficiency. Now, at this stage we can simplify this further, because we know that between 1 and 2 we have assumed an isentropic process. That means PV to the power k or PV to the power gamma. In certain books you will read the coefficient as gamma. Here I have used k, for example, a generic term or polytropic term. In certain books it is n. Don't get confused on this. It represents the index of compression. So, here you will see T1 upon T2 is equal to V2 upon V1 to the power k minus 1, which comes directly from the definition of the isentropic process, where the PV to the power k is always a constant, and you can easily get this expression, which is, since V2 is equal to V3, okay, and V1 is equal to V4, because we have both these things at constant volume. So, at constant volume V3 is equal to V2 and V4 is equal to V1. You can substitute that. So, therefore, you will see that T1 upon T2 comes out to be, the ratio comes out to be equal to T4 upon T3, and with the definition which we have already done for the compression ratio, that is the V max divided by V min the ratio of these two, which is nothing but V1 divided by V2. V1 is corresponding to the volume at BDC, and V2 corresponds to the volume at TDC. So if you take this ratio, we have already defined the let us say R, the compression ratio R. So if you substitute this 2 in the equation which we have obtained for the efficiency, you will get a very good simplified expression for the efficiency of the Otto cycle, which is 1 minus 1 divided by a compression ratio to the power k minus 1 or gamma minus 1. So an elegant expression for the efficiency of the Otto cycle comes. Now as you can clearly see, the efficiency of the Otto cycle here is a function of the compression ratio R and the index of compression K. So let us try to plot this and see how the compression ratio affects the efficiency of the Otto cycle. So coming to this effect of the compression ratio here, as you can see, this is our expression 1 minus 1 divided by R to the power k minus 1, and if I fix a k, let us say if I fix k to be 1.4, let us say for an ideal monoatomic gas, okay, for an ideal system, if I assume k to be equal to 1.4 and then I see the effect of changing R. So let us say the R changes from some value here, a low value of 1 to let us say up to 14, and what do we see? We see very clearly that the efficiency of the Otto cycle directly depends on the compression ratio. Naturally, initially the rate of rise is pretty high and then later on it tapers off, and I have also mentioned here the typical compression ratio of the gasoline engine. Now why do we operate between this and this? Why can't we go higher than this? So this is the answer lies in the fact what type of fuel you are burning and whether that fuel can sustain high compression ratios. So we will study when we are talking about the characteristics of the fuel. At that time you will notice that in SI engines the compression ratio is limited by the auto ignition or the engine knock. That means we would typically like to have this compression ratio high because we are typically getting good efficiency, let us say 70% efficiency at compression ratio of 14. But the problem is that in an Otto cycle, which is a petrol based cycle, wherein we want the heat to be added very quickly, if you increase the compression ratio beyond a particular value, then what will happen is that this fuel will start, let us say, auto ignition or abnormal ignition. That means the temperature and pressure, because as the compression ratio increases, naturally the pressure, the highest pressure which is in the cycle, okay, will increase. That means this pressure P3, P2 will increase, and naturally then the P3 will go further high when the fuel comes in, and therefore if the temperature and pressure are high as the compression ratio increases and the fuel starts let us say behaving abnormally, that means the combustion process which we would like to have a certain control on and in a certain way we would like to do the combustion dynamics, if that is failing or that is becoming abnormal for certain reasons which we will discuss in a separate lecture, then naturally we will not be able to let us say operate that particular fuel. So the fuel, actually the quality of the fuel, the way it burns, the way the combustion dynamics takes place, that necessarily decides the maximum compression ratio which is obtainable or which is tolerable in a particular engine. So typically, as you are seeing on this graph, the compression ratio of petrol engines lies between, let us say, 7 to up to 10 or 11. So not higher than that. So this is a typical range, and we will discuss that in the next lectures of why this range is sort of limited by the type of fuel which we utilize. So now one more aspect which we should cover is the effect of the compression, the index of compression, which is the K. So typically for an ideal gas it is 1.4, but I have shown here two graphs wherein you see that the thermal efficiency of the Otto cycle increases with the specific heat ratio K of the working fluid, that is this K is Cp divided by Cv, as you all know. So if Cp by Cv changes And now in an ideal situation, if you are just taking air as a cycle or air as a medium, then K is not going to change. However, if you will recall that in an actual engine, the intake is a mixture of air and fuel, and the outlet is a mixture of carbon dioxide, steam, nitrogen oxides, and some nitrogen, some unburnt fuel. So naturally, as the cycle goes in a real cycle, the specific heat of the intake air and the specific heat of the gases, the specific heat of the mixture are all changing with temperature, and and since the specific heats are changing, their ratio Cp upon Cv also changes. So you see that if the specific heat ratio K is higher or the index of compression is higher, you get a better efficiency of the Otto cycle. So with this we conclude this lecture. We have introduced you to the Otto cycle and its basic, how you can calculate the efficiency of this cycle and how the efficiency depends on the compression ratio and the index of compression or the ratio of the specific heats Cp upon Cv. So I strongly recommend that you go back and revise some of your older thermodynamics lectures so that you get very conversant with the ideal Otto cycle, because our subsequent discussions on real cycles will actually depend on this background which we have just created.